Hello everyone, myself Arithro Maiti. I am from Coachbihar Government Engineering College and I am a student of second year electrical engineering. Today I am going to present a PPT on the diode operation characteristics. Welcome to this in-depth video on diodes, one of the most essential components in modern electronics. Diodes play a critical role in almost every electronic device we use today. They are semiconductor devices that allow electric current to flow in only one direction, making them incredibly important for controlling and regulating the flow of electricity in circuits. Imagine you have a one-way street where cars can only travel in a single direction. Diodes work similarly by allowing current to pass through in one direction while blocking it in the other. This property is what makes them indispensable in various applications such as converting alternating current or AC to direct current or DC. Throughout this video, we'll explore the characteristics, types, and real-world applications of diodes, helping you gain a solid understanding of why these components are so crucial in the field of electronics. Now that we've introduced the concept of diodes, let's dive into what a diode actually is. The term diode comes from di meaning two and ode referring to electrodes. Hence, a diode is a device with two terminals, an anode and a cathode. But what sets a diode apart from other electronic components? It's the one-way flow of current. When voltage is applied across the diode in the correct direction, it allows current to flow from the anode to the cathode. However, if the voltage is reversed, the diode blocks the current, acting like a closed gate. This unique characteristic is what makes diodes so valuable. For instance, they are used in power supplies to convert AC-DC, ensuring that devices receive a steady, unidirectional flow of electricity. Without diodes, our electronic devices wouldn't be able to function properly. In summary, diodes are the gatekeepers in electronic circuits, controlling the flow of current and protecting sensitive components from damage. Let's now take a look at how diodes are represented in circuit diagrams. Understanding these symbols is crucial for anyone working with electronic circuits, as they provide a quick way to identify the function of each component. The symbol for a diode is quite simple. It consists of a triangle pointing towards a line. The triangle represents the anode or the positive terminal, while the line represents the cathode or the negative terminal. The direction of the triangle's point indicates the allowable direction of current flow from anode to cathode. This symbol is not just a visual representation, it encapsulates the fundamental operation of the diode. When you are reading a circuit diagram, seeing this symbol immediately tells you that this component will only allow current to flow in one direction, which is crucial for the circuit's operation. Understanding this symbol is the first step in decoding and designing electronic circuits that incorporate diodes. To understand how a diode functions, we need to explore its internal structure. Diodes are made from semiconductor materials, typically silicon, although other materials like germanium can also be used. At the core of a diode is the p-n junction, which is formed by joining two types of semiconductor materials, p-type and n-type. The p-type material is rich in holes, which are essentially the absence of electrons and carry a positive charge. On the other hand, the n-type material has an abundance of electrons, which carry a negative charge. When these two materials are brought together, something interesting happens. Electrons from the n-type material move towards the p-type material to fill the holes. This movement of charge carriers creates what is known as the depletion region, a region where there are no free charge carriers. The p-n junction is the heart of the diode's operation. It's where the diode controls the flow of electricity, allowing current to pass through in one direction while blocking it in the other. This simple yet effective structure is what makes diodes so versatile in electronic circuits. Diodes come in various types, each designed for specific applications. Understanding the differences between these types is essential for selecting the right diode for your circuit. Standard diodes, these are the most common type used in general purpose rectification. They convert AC to DC which is crucial for powering electronic devices that require a steady DC supply. Zener diodes. Unlike standard diodes, Zener diodes are designed to operate in reverse bias mode. When the reverse voltage reaches a certain level, called the Zener voltage, the diode starts conducting in the reverse direction. This makes Zener diodes perfect for voltage regulation, ensuring that a circuit receives a stable voltage regardless of fluctuations in the power supply. Light emitting diodes. LEDs are a special type of diode. Diode emits light when current flows through them. They are widely used in displays, indicators, and lighting because of their efficiency and long lifespan. Schottky diodes. Known for their low forward voltage drop, Schottky diodes are ideal for high-speed switching applications. They are commonly used in power supplies and RF applications where efficiency and speed are crucial. Photodiodes. These diodes generate current when exposed to light, making them essential in light detection and solar power applications. Photodiodes are used in cameras, light meters, and other devices that require light sensing. Each type of diode has its own unique characteristics and applications, making diodes one of the most versatile components in electronics. The p-n junction is the core element of a diode, and understanding its basics is crucial to grasping how diodes function. When the p-type and n-type materials are brought together, electrons from the n-type region start moving towards the p-type region, filling the holes. This process creates the depletion region, a zone around the junction where there are no free charge carriers. But why is this depletion region important? It acts as a barrier that prevents the free movement of electrons and holes across the junction. In other words, it blocks the current from flowing in the reverse direction, which is a key characteristic of diodes. The depletion region also creates an electric field, which opposes the further diffusion of charge carriers. This electric field is what gives the diode its rectifying properties, allowing current to flow in only one direction under normal circumstances. Understanding the p-n junction is the first step in mastering diode technology, as it explains the core principle behind their operation. When we talk about the p-n junction, we have to consider the concept of barrier potential. The depletion region, which we just discussed, creates an electric field that opposes the movement of charge carriers. This electric field is associated with the potential difference known as the barrier potential. The barrier potential is essentially the voltage needed to overcome the electric field of the depletion region and allow current to flow through the diode. For a typical silicon diode, this barrier potential is approximately 0.7 volts, while for germanium diodes it's about 0.3 volts. This means that if you apply a forward voltage less than the barrier potential, the diode won't conduct. Only when the applied voltage exceeds the barrier potential does the diode allow current to pass through. This property is crucial for understanding how diodes function in circuits, as it determines the conditions under which the diode will conduct or block current. Before we apply any external voltage to a diode, the p-n junction reaches what is known as an equilibrium state. In this state, the diffusion of electrons and holes across the junction is exactly balanced by the electric field of the depletion region. This balance means that no net current flows through the diode and the junction remains stable. Why is this equilibrium state important? It ensures that the diode remains non-conductive until an external voltage is applied. Understanding this state is crucial for designing circuits that rely on the diode's ability to control current flow based on the applied voltage. Let's now explore what happens when we apply a forward bias to a diode. In forward bias, the anode is connected to the positive terminal of a power supply and the cathode is connected to the negative terminal. This setup reduces the width of the depletion region, effectively lowering the barrier potential. As a result, once the applied voltage exceeds the barrier potential, typically 0.7 volts for a silicon diode, current starts to flow through the diode. The more the forward voltage increases, the more the depletion region narrows, allowing even more current to pass. In practical terms, forward biasing is how we get a diode to conduct electricity in a circuit. It's essential for applications like rectification, where we need to convert AC to DC by allowing current to flow in only one direction during each half cycle of the AC signal. Reverse bias is the opposite of forward bias. Here the anode is connected to the negative terminal and the cathode to the positive terminal of the power coil supply. This setup widens the depletion region, increasing the barrier potential and effectively preventing current from flowing through the diode. However, if the reverse voltage applied to the diode exceeds a certain threshold, known as the breakdown voltage, the diode will start conducting in the reverse direction. This can lead to a significant increase in current, which might damage the diode if not properly managed. This reverse bias operation is utilized in specific diodes like Zener diodes where the breakdown characteristic is exploited for voltage regulation. But in most cases, the reverse bias is used to block current, protecting the circuit from potential damage. Zener diodes are a special type of diode designed to operate in the reverse breakdown region without getting damaged. When the reverse voltage applied to a Zener diode reaches the Zener breakdown voltage, the diode conducts in reverse, but the voltage across the diode remains constant. This characteristic makes Zener diodes perfect for voltage regulation. They are commonly used in power supplies to ensure that the output voltage stays within a specific range, even if the input voltage fluctuates. For example, if you have a 5V Zener diode, it will maintain a 5V output as long as the input voltage is higher than 5V, regardless of any variations. This makes Zener diodes indispensable in designing stable power supply circuits. Temperature plays a significant role in the operation of diodes. As the temperature increases, the barrier potential decreases, making it easier for current to flow through the diode. However, this can also lead to a phenomenon known as thermal runaway. Thermal runaway occurs when an increase in temperature leads to an increase in current, which generates more heat, further raising the temperature and so on. This positive feedback loop can cause the diode to overheat and potentially fail. To prevent thermal runaway, it's important to manage the temperature of the diode either through heat sinks, proper ventilation, or by ensuring the diode operates within its specified temperature range. Understanding the impact of temperature on diodes is crucial for designing reliable circuits that operate safely under various environmental conditions. Diodes, especially when reverse biased, exhibit a property known as junction capacitance. This capacitance is due to the depletion region acting like the dielectric of a capacitor, with the p-type and n-type regions acting as the plates. As the reverse voltage increases, the depletion region widens and the capacitance decreases. This property is utilized in varactor diodes, which are used in tuning circuits like those found in radio frequency oscillators. By varying the reverse voltage applied to a varactor diode, the capacitance changes, allowing the circuit to tune to different frequencies. This principle is what makes varactor diodes so valuable in communication systems, where precise frequency control is essential. Diodes have a wide range of applications across various fields of electronics. Here are a few key examples. Rectification diodes are crucial in converting AC to DC in power supplies, ensuring that electronic devices receive a stable, unidirectional current. Signal demodulation in communication systems. Diodes are used to extract information from modulated signals, converting them back into their original form. Voltage regulation Zener diodes are commonly used in power supplies to maintain a constant voltage, protecting sensitive electronic components from voltage spikes. Light emission LEDs are used in displays, indicators, and lighting. Their efficiency and long lifespan make them ideal for a wide range of applications, from consumer electronics to industrial lighting. Light detection photodiodes are used in cameras, light meters, and solar cells. They convert light into electrical energy, making them essential in any application that requires light sensing. These examples highlight the versatility and importance of diodes in modern technology. Whether it's powering your devices, lighting up displays, or detecting light, diodes are at the core of many electronic systems. To see diodes in action, let's consider a few real-world examples. Power supplies in almost every electronic device. From your smartphone to your computer, diodes are used to convert the AC power from the wall outlet into the DC power required by the device's internal circuits. LED displays, whether it's the screen on your phone or the indicators on your microwave, LEDs are everywhere. They provide bright, energy-efficient lighting and are a direct application of diode technology. Solar panels photodiodes are used in solar panels to convert sunlight into electrical energy. This technology is key to generating renewable energy and reducing our dependence on fossil fuels. These examples demonstrate the crucial role that diodes play in our everyday lives, often in ways we don't even realize. Understanding these applications helps us appreciate the technology that powers the modern world. In conclusion, diodes are one of the foundational components of electronic circuits. Their ability to control the flow of current makes them indispensable in a wide variety of applications, from simple rectification to advanced communication systems. By understanding the characteristics and behavior of diodes such as forward and reverse bias, breakdown phenomena, and temperature effects, you can design more efficient and reliable circuits. I hope this video has provided you with a deeper insight into the world of diodes and their essential role in electronics. Thank you for watching, and if you found this video helpful, don't forget to like, share, and subscribe for more content on electronics.